Now we will study logistic regression. In this session, we study the basic form of dichotomous logistic regression model. It is important to understand special mathematical advantages of the model, in comparison with some alternative modeling possibilities. Suppose you have data from a large health survey. The dataset includes several variables that seem interesting as the dependent variable for multivariate analysis. Now that you have learned multiple linear regression, you may feel that you can do various multivariate analyses with the data. But you may find that multiple linear regression is not applicable to many of those dependent variables. Why? Because many of those variables were categorical, such as whether a person had become hypertensive or not during a follow-up period, and whether the person is diabetic, pre-diabetic, or neither. These variables are not numerical, so we cannot apply linear regression to them. What kind of regression model can be developed for a categorical dependent variable? Let's start with the linear regression model and modify it for a categorical dependent variable. Let's start with the relatively simple form of the categorical variable, that is, a dichotomous variable. Since a dichotomous variable has two exhaustive and mutually exclusive categories, it can be considered as occurrence versus non-occurrence of some event. So, we can think of it in terms of a probability for the event to happen. The probability, p, should differ among individuals, so the subscript I could be attached for an individual I. Therefore, the dependent variable of a linear regression, y sub I, may be replaced by p sub I, as shown here. Now, in this model, the probability for individual I to experience some event is estimated from a linear combination of some characteristics of the individual. This is the equation from the previous slide, which models the probability of the event as a linear combination of selected characteristics. But this model has some mathematical problem. What is that? The left-hand side of this equation is a probability which must be between 0 and 1. The right-hand side is a linear combination of some variables, which could take any value between -infinity to +infinity. So, the combination of the estimated values of alpha and beta, and data on x's could produce a negative value or a value greater than 1, as an estimate of the probability. Still, sometimes, the model is used and adopted, when the estimated probability is between 0 and 1, for every individual in the data. It is called the linear probability model, and an estimated beta value could be straightforwardly interpreted as the change in probability of the event, corresponding to a unit increase in x. But even if the estimated model produces probabilities between 0 and 1, for each case in the data, it still may produce estimated probabilities outside the range, when it is applied to cases outside the data. Many researchers are unwilling to use this model because of the logical defect in the mathematical form. Will the problem be solved if we use the natural logarithm of the probability instead of the probability itself? ln, on the left-hand side of the equation, means the natural logarithm, that is, the logarithm to the base e. A log probability is a negative number or 0. But since the maximum value of a probability is 1, and the log of 1 is 0, a log probability cannot be a positive number. However, the mathematical form on the right-hand side has nothing to keep its value from being positive. This model could produce a positive number as an estimate of log probability, which is contradictory. Nevertheless, some researchers use this model, which is called relative risk regression, because the estimated beta values may be straightforwardly interpreted as effects of x's on the relative risk of the event. Its computer program usually includes an algorithm that avoids a positive number as an estimate of log probability for any case in the data. But a number of researchers do not want to use this method, because the computer programs of relative risk regression avoid a positive value of log probability only in an ad hoc manner, also because the estimated model may produce a positive value of log probability when it is applied to cases outside the data, and because the mathematical form has the logical defect that a positive value could be produced as an estimate of log probability. Then, how about using odds instead of probability or log probability? Odds are the ratio of the probability for an event to occur to the probability for an event not to occur. Odds could be a positive value or 0 but cannot be negative. Since both the numerator and denominator of odds are probabilities, odds must be non-negative. But the mathematical form of the right-hand side has nothing to prevent it from producing a negative estimate of odds. Then, how about the log odds? Now, both sides of the equation could be any positive or negative value. This is the basic form of logistic regression model which is widely used for regression analysis with a categorical dependent variable. It is also called logit regression because log odds are called logit. We saw that in the previous models the range of values on either side of the equation did not match. With the log odds, this logical defect is eliminated by modeling the logit on the left-hand side and using a linear combination of variables on the right-hand side. This graph shows the relation between odds and log odds, around odds of 1. The downward curve approaches the vertical line for odds of 0, but the curve never passes the line, indicating odds could not be negative. As seen in this graph, log odds keep rising to the right, toward positive infinity, and keep falling to the left, toward negative infinity. So, log odds could be any positive or negative number. Note that the curve crosses the horizontal dotted line, at which the value of odds is 1 and that of the log odds is 0. This is an important point that indicates when the probability is 0.5, the odds are 1 and the log odds are 0. An example use case for the logistic regression model and prediction is deciding whether email is spam or not. Based on a linear combination of the features that an email contains, that is, whether it mentions certain keywords or even large sums of money, the higher the probability that the email is spam. The decision is made based on a predicted probability value cutoff. Logistic regression is not the only regression model for a categorical dependent variable. There are some alternative methods that are widely used. They include probit, which uses normal distribution, and complementary log-log, which could be used for modeling hazard, which is another measure of chance, as a linear combination of factors. In the old days, before development of these models, the discriminant function analysis was the most widely used method for a categorical dependent variable. In public health research these days, logistic regression is probably the most widely used regression method for a categorical dependent variable. There are different variants of logistic regression, and different names for them. If the dependent variable has just two categories, the logistic regression is dichotomous logistic regression, which is also called a binary logistic regression. If there are three or more categories, a polytomous logistic regression is used. If the dependent variable has three or more categories that have an intrinsic logical order, an ordinal logistic regression or ordered logistic regression may be used. For example, diabetes-related categories may be ordered as diabetes, prediabetes, and no diabetes. Dichotomous logistic regression is also called binomial logistic regression, and polytomous logistic regression is also called multinomial logistic regression. These two names are widely used, and they come from names of two probability distributions, binomial distribution and multinomial distributions. But usually those probability distributions are not used. In computational processes of those logistic regression analyses, the names of dichotomous logistic regression and polytomous logistic regression are used in this course. If we compare the linear regression and logistic regression models, we note that there is essentially just one expression of the linear regression model, which is the equation at the top of this slide. But the logistic regression model can be expressed in three different ways. It models log odds as a linear combination of x's. Then the odds are the exponential function of the linear combination of x's. And the probability is expressed in this form, which is a logistic function of the linear combination of x's. These three forms are mathematically equivalent, and any one of them can be derived from each of the other two. The three forms can be visualized as these three graphs. For all of the three panels, the horizontal axis is the value of the linear combination of x's. The top panel shows the log odds as a linear function of the linear combination. This is a special linear function, with a slope of 1 and through the point of origin, that is, the point x and y coordinates of which are both 0. The second panel shows the odds as an exponential function of the linear combination. And the third panel shows the probability as a logistic function of the linear combination. The logistic function is an S-shaped curve that has the lower and upper bounds, which are 0 and 1, in the case of the logistic regression model. The three forms of logistic regression model can be derived from each other, as shown here. The derivation is a set of fairly simple algebraic manipulations, and it is strongly recommended that you go through them when you have time, which will help to understand mechanics of the logistic regression model. Odds are, by definition, the ratio of probability to 1 minus probability, or the ratio of the probability for the event to occur, to the probability for the event not to occur. So odds are defined in terms of probability, but it is useful to know that conversely, probability can be expressed in terms of odds. As derived here, probability is the ratio of odds to 1 plus odds. Now, let's look at an example of logistic regression analysis. The NHANES data used for most of previous examples in this course are used again. The dependent variable is self-reported general health condition. This is based on responses to questions about general health condition of the respondent, who was asked to select among 5 choices: excellent, very good, good, fair, and poor. So originally the variable had 5 categories, which were grouped into 2, by combining fair and poor together as not healthy, and also excellent, very good, and good together as healthy. The log odds of not being healthy were modeled as a function of gender, age, race, ethnicity, education, and marital status. Data on those aged 20 to 84 were used, but probably the range should have been from 25 to 84, to exclude college students aged 20 to 24. Estimated values of regression coefficients, or beta coefficients, are shown in the column labeled B of this table. Their p-values are shown in the column titled SIG. The column labeled as XP shows exponentiated values of the coefficients, which are important in interpreting the results, and will be discussed in more depth in the next session. The reference categories are male, non-Hispanic white, college graduate, and currently married. Note that, as in linear regression, beta values for the reference categories could be considered as being fixed at 0. So the table shows, controlling for the other independent variables, females tend to have slightly higher chance of being self-reportedly unhealthy than males, but its p-value was large. Hispanics had the greatest chance of being self-reportedly unhealthy, followed by non-Hispanic blacks and others, and then non-Hispanic whites. Lower levels of education were associated with higher chance of being self-reportedly unhealthy. As for marital status, the widowed or separated are the group of highest chance of being self-reportedly unhealthy. Now the model can be shown as this equation, into which estimated values of the coefficients have been incorporated. For each respondent, by substituting values of the binary and numerical independent variables into this equation, we can obtain an estimated value of log odds for the respondent to be self-reportedly unhealthy. Let's put the data for a respondent into the estimated equation. The respondent is a 70-year-old, widowed, non-Hispanic white man who had not graduated from high school. By substituting his values into the equation, we get minus 0.674 as an estimate of his log odds of being self-reportedly unhealthy. Substituting minus 0.674 into the logistic function form, his probability of being self-reportedly unhealthy is estimated to be 0.338, that is, 33.8%. In linear regression, usually alpha and betas are estimated by OLS, which is not used for logistic regression, because the dependent variable is not a numerical variable. OLS can be considered as a variant of maximum likelihood estimation, tailored to linear regression, under the 4 assumptions used for statistical inference for linear regression. Maximum likelihood estimation is a general principle of estimation of parameters of statistical models. In logistic regression, a variant of maximum likelihood estimation tailored to the logistic regression model is used for estimating alpha and betas, under the assumption of independence among the probabilities for different cases. Explanation of mechanics of the maximum likelihood estimation for logistic regression is beyond the scope of this session. But, if the maximum likelihood estimation is applied, we can expect to have the following type of results. Suppose that for some respondents, the probability to experience the event, denoted here as P, was estimated to be around 0.1, that is, 10%, based on their values of the independent variables. Then, the proportion of those respondents who actually experienced the event, denoted as R, should be about 10% as well. Likewise, among respondents whose estimated probabilities are around 0.2, the proportion of those who experienced the event should be about 20%. And among respondents whose estimated probabilities are around 0.3, the proportion of those who experience the event should be about 30%. Let's check if this expectation is met in results of the logistic regression of self-reported general health. In this graph, the horizontal axis is the estimated probability of being self-reportedly unhealthy. The vertical axis is the proportion of those who actually reported that their general health conditions were poor or fair. Each asterisk represents a group of respondents whose estimated probabilities were in a 0.05 point range. For example, the leftmost asterisk represents the respondents whose estimated probabilities are from 0 to 0.05, and the next asterisk represents the respondents whose estimated probabilities are from 0.05 to 0.10, and so on. Most asterisks fall near the red diagonal line, indicating the estimated probabilities and actual proportions are very close. There is one outlier, which is the asterisk on the upper frame of the graph, but this group has only one respondent. So this graph may suggest that the probability of being self-reportedly unhealthy was estimated from the 5 demographic and socioeconomic characteristics quite well, using logistic regression.